Hi, everybody. Dr. L here with another segment. And in this segment, we're going to talk about an important algorithm to understand the context, rather the greater context of machine learning. And that is something called the bisection method or the bisection algorithm. And this is going to be a building block for us to think about when we move to a slightly more complicated framework where we have multiple parameter values to estimate in higher dimensions, where we will use something called the gradient descent algorithm. But let's go ahead and jump into the material related to the bisection method. First and foremost, we're going to understand why we are going to use iterative methods or iterative procedures. Why can't we just take the first order condition of the cost function and find a solution analytically like we did for the pseudo-inverse estimator using linear regression? Why can't we do that in every case? And the short answer to that is not every problem is as well defined as the linear regression problem was when we were minimizing the sum of squared residuals. Next, we'll talk about the elements of an iterative algorithm. There are really four important components to understand. Every algorithm has these four components that you'll need to specify here. And we're going to go through these elements in the context of the bisection method, which is specifically a univariate method that we're going to look at here, meaning there's just one variable, one choice variable in the problem. We're going to think about minimizing the cost function in just one dimension with respect to that particular choice variable. So it is a one-dimensional problem. And we're going to take a look at the update rules, the stopping rules for understanding how this algorithm works is kind of a foundational step towards the gradient descent algorithm. So why use iterative methods? Why do we do this? Well, recall in the case of linear regression, we actually had a one-step analytical solution to the cost minimization problem, right? We tried to minimize our in-sample error function. That in-sample error function was U transpose U is the sum of those squared residuals. And what we were able to do here was actually write out the optimization problem. We took the derivative, the first order conditions, we set it equal to 0, and we could find the pseudo-inverse estimator here, which recovered for us all of the betas in just one step. So that pseudo-inverse matrix was this matrix in red here, X transpose X inverse times X transpose. And all we had to do was essentially take that X matrix after specifying what it was, plug it into this formula here, multiply it by our Y vector, and then boom, we were able to recover the parameter estimates that minimize that cost function in one step. So all the user had to really do here was describe the model, specify the X matrix and the Y output data in order to retrieve these parameter estimates. Even if the user didn't know any calculus and didn't know how they got the solution, they could still just plug in the values of the X matrix and the Y vector. Now, why use iterative methods? Well, not every problem has this nice property in that it yields an analytical closed form solution. Okay, there are many algorithms, many models we can estimate that do yield closed form solutions, but I would say there's an even larger class of problems that do not. So linear regression, this was really a special case of a situation where the cost minimization problem did have this nice property where there was an explicit analytical solution. But many other problems do not share this ideal characteristic. And in the case where a problem does not have an explicit analytical solution, typically what this requires us to do is invoke some sort of computational method or some sort of numerical method in order to approximate a solution or in order to get sufficiently close to the solution. And in order to do this, we're going to take advantage of the fact that we have a computer at our disposal, right? In analytics, the big benefit of understanding analytics is that we know when to hand off the heavy lifting to the computer, because the computer has limitless capacity for iterative computations, essentially, not really limitless, but compared to humans, the computer can process much more information in a way shorter amount of time than we can, in a way where the computer is able to do things like make incremental changes and check to see whether or not a solution has improved or worsened, right? If you had a person just randomly plugging in numbers and checking, did that minimize this function or not, would take a very long time because people are pretty slow at this. But the computer can make these incremental checks and improvements to the solution to see whether or not we're improving our guess at where we think a particular optimum is. Now, what are these four important elements of an algorithm? They are the following. First thing we have is the initialization step. And the initialization step is going to define for us what we're going to refer to as the initial guess for our search parameters. Okay, so this is how we kind of start things off. We get the ball rolling, we initialize, we pick some initial guess for our parameter estimates. And then maybe the most important element of the four are iterations. Iterations are recursive repetitions that are used to improve the guess by checking some condition regarding the cost function and using that condition to inform an improvement of our parameter guess via an update rule. Which brings us to element 3, which is the update rule. The update rule is a computation that's going to link a previous iteration's parameter guess to the updated iteration's parameter guess. So this is going to link, really create a rule rather, that links how we improve the guess from one iteration to the next. And last but not least, we are going to have something known as a stopping rule criteria, which is criteria that must be satisfied when we believe our guess is sufficiently close to the actual optimal parameter value. Now, this is somewhat of a catch-22 because we don't really know what the optimum is. Okay, so we're kind of going to be driving blind here in that. In many cases, we know we have a cost function, but it's maybe difficult to compute. There might not be an analytical solution that defines the optimum, but we can still compute the derivative at a point. So the question is, when you're flying blind like this, how do we know when we are sufficiently close to the optimum? And I think the best way to really understand this is to take a look at the bisection algorithm, which is a one-dimensional cost minimization problem. Okay, and again, our goal here is to figure out along the horizontal axis, what is the correct parameter estimate for beta? Right? What is the correct value of our betas that will put us at the very bottom of our cost function? We don't want to be over here. We want to move to the very, very bottom of that cost function. We don't want to be too far to the right. We want to move to the bottom. So that is the problem. Okay, we want to choose the beta to identify the bottom of this cost function. And in most cases, we wouldn't be able to graph it like we can here in one dimension, right? If we have, a parameter or a problem where we have to estimate 20 different beta values, and that's going to be, at least a 20-dimensional problem, which we cannot graph. So we wouldn't really have this visual representation to help us here. You might say, if we did, why do we need the iterative approach? I can just plot the cost function and I can zoom in on that minimum, and you would be right, you could. But most cases are higher dimensions. So we're going to think about this problem here of finding the parameter estimates that minimize this cost function. So that is the problem we're solving. We're still solving cost minimization, okay, as defined by some in-sample error metric or some maybe augmented cost function, right? So this cost function up here could be, calculated by some error metric that we had talked about, the sum of squared errors, the mean square error, maybe the root mean square error. So the goal is to find the parameter value that gives us the best fit in terms of minimizing this cost function, right? And that will happen here at the very bottom. Okay, and again, this is going to be a little catch-22 in that we can see this diagrammatically where that minimum is, but I want to do this to convince you how the algorithm is actually going to work. So again, we're going to simplify the analysis here. We're going to consider a problem where we're estimating some model where we only have one beta parameter. So for example, if you had a regression model with one X variable and no intercept term, this would fall into this particular category. And we're going to start off here by initializing the problem. We're going to go ahead and choose a guess. And the guess in the bisection algorithm turns out to actually involve us specifying a window within which we expect the right beta value to fall. Okay, so we're going to specify here a lower bound and an upper bound in between which we believe that the optimal value of beta star falls. And one situation that can immediately go wrong here is we could choose a range of the lower and upper bounds here, beta L and beta U, okay, where it doesn't contain the interval. But you'll notice here with this particular choice that we're looking at, right? We have our lower bound, we have our upper bound, and they definitely do contain beta star as the optimal value here. They do contain it. And because of that, this algorithm will actually converge to the minimum after a certain number of iterations. But you could mess up immediately. For example, if we set beta u, the upper bound value, over here, okay, then what would happen is we would wind up searching in a region along the x-axis only in between the lower bound and the upper bound. And we would actually miss out on the optimal value of beta, which occurs in the middle of this function, at the minimum. So first step here, we have to initialize. We have to set our upper and lower bounds. And I'm going to use the subscript 0 here, okay, to denote the iteration number we are on. So we're starting off with iteration 0, right, our initial guess here. And our initial guess is being defined here by setting the upper and lower bounds. Okay, so beta 0L and beta 0U are going to define for us the bounds by which we construct our initial guess. And this algorithm is called the bisection algorithm for a very important reason, and that is at every iteration, we're going to take these bounds and we're going to cut them in half. We're going to bisect them, okay, and we're going to do that here by constructing our initial guess B0 as literally the bisection of this interval. Okay, we're bisecting the upper and lower bounds, which means we're going to add them. We're going to divide by 2. We're going to take the linear average. Okay, so here is us doing that bisection. So B0, our guess in period 0, right, is a function of our initialization guesses, the upper and lower bound, and that's going to bisect that region right here. Okay, so what did that do? Well, that bisected this region into 2 regions now of equal size. This distance and that distance are of equal size because beta 0 with the 0 superscript, that bisects beta u and beta l. Okay, so we're considering here our first iteration, iteration 0. And in order for us to advise on where to move, we can sort of tell here that our initial guess of beta 0 is not the optimum, right? It's a little bit too far to the left. So we have to think about how to update this guess. And the way we're going to update this guess is we're going to compute the slope of the cost function at this particular value. All right, so we're going to take this value B0, we're going to plug it into the cost function, and we're going to compute the slope at this particular point. That is what we are going to do here. So when we do that, right, what's the slope of the cost function? Well, it's the derivative of the cost function. That's what we would be calculating here, and we could do this. We have the math to do that. Okay, so we have the computer, right? We pass it the expression for the derivative. The computer calculates it. And we can see here graphically that that derivative, right, the slope of the tangent line is negative in this case. And I'm going to argue that that's important because it informs us that we must be too far to the left. And if we're too far to the left of the optimum, okay, the function is downward sloping in that region. So identifying the sign of the slope of the function is going to help us guide our update rule here. So at iteration 0, what do? We check the slope. And we noticed that the slope at our first guess, B0, beta 0, that is negative. And again, that's useful information because it tells us that the actual optimum value here that we're searching for is a little bit farther to the right. Okay, there's the optimum value. So we have a little bit of error on our first guess. And we want to adjust accordingly. We want to reduce that error. Okay, so the way we're going to do this is by essentially picking up one of our bounds, okay, and moving the goalposts. So we had 2 bounds here. We had the lower bound and we have the upper bound. What we're going to wind up doing is picking up one of those bounds and moving it, okay, and then recomputing our bisection. Okay, that is how we're going to approach this. You'll note that we could move the left bound or the right bound, and it turns out in this situation, it's actually going to be optimal for us to move the left boundary point B0 farther over to the right in order to push our guess farther to the right. So let's go ahead and apply this update rule here. We're going to improve our guess for the next iteration. So we're trying to improve our guess for B1, right, the guess on the next iteration. And we're going to do this by moving the left boundary further to the right. We're going to move the left boundary point, BL, further to the right than it was in iteration 0. And we're going to do this by taking that boundary point, and we're literally going to move it to where B0 was in the first iteration. Okay, so our lower bound in the next iteration, what is that going to be? It is going to be B0 from the previous iteration. That's what we're going to do. So we're going to move that left goalpost to the right. Okay, and for now, we're not going to move the right goalpost. We're going to keep B0U where it was. So the right upper bound is going to stay the same in the next iteration. So here's literally what we are doing, right? We're taking B0L and we're moving it farther to the right so that in the next iteration, B1L is taking the place of where B0 is. Okay, and B1U at iteration 1, we're going to keep that the same. So notice when we do this, our search window, it started big. Okay, but now we've updated that search window and we've made that window smaller. Okay, and note that beta star still falls within that window. So we're doing a good job here. Okay, we're doing a good job. So here is what we're going to do. We're going to take those updated boundaries and we're going to now replace them. These are going to be our new boundaries for the problem. And what do we do now? Well, we are now in iteration number 1. Okay, we've left iteration 0. We've updated our boundaries. And now we're going to go ahead and with iteration 1, we're going to compute our guess B1, which again is going to bisect B1L and B1U. Okay, so again, beta 1 here, our guess at iteration 1 is halfway in between those points. And we're going to do the same thing. Okay, how good is that guess? Well, let's check the slope. Okay, and we can recognize the slope at B1 here, at beta 1, is actually positive. Okay, we have an upward sloping part of the function, and that is also informative for us. Okay, recognizing that slope is positive tells us that the actual solution is now on the left side of our guess. Okay, we need to move to the left of beta 1 here. Right? And here's a peek at the solution, right? There's beta star, it's a little bit to the left. Okay, and again, understanding the slope information here is critical, right? So the computer is checking the slope at our guess in every iteration, and it's using that slope information to guide the update rule. So in the last situation, when we had to move farther to the right, we picked up the left goalpost and we moved it further to the right. But now we need to move further to the left. So our update rule is essentially going to take the right goalpost and we're going to now move that farther to the left in order to improve our guess, in order to apply that update rule here. Okay, and again, goal is to get closer to beta star, right? That is the goal. We want to move closer to beta star. And it looks like we're starting to close in, right? We have a little bit of error here. Okay, but note that's smaller error than we had relative to the guess at iteration 0. So let's go ahead and apply our update rule. Okay, we want to move a little bit to the left, and we're going to do this now by picking up that right boundary point and moving that right goalpost further to the left by setting it equal to beta 1 in the next iteration. So the next iteration, okay, in iteration 2, we're going to move the right goalpost, the upper bound, to where beta 1 is now. Okay, so we're moving that goalpost to the left, and we're not going to move the left goalpost. We're not going to move the left boundary this time. So beta 2's lower bound is going to be equal to the same lower bound that we had in the first iteration. Okay. Again, note here that we have, again, reduced the search interval, right? In iteration 1, here was our search interval defined by the length of that green double arrow, and we've now compressed that further. Okay, so every single iteration, what's happening? Our upper and lower bounds compress around the optimum, and we get a slightly improved guess by bisecting that region here. So let's go ahead and compute the guess now at iteration 2. We have our lower and upper bound. We can take the average of the lower and upper bound to get beta 2 here, and that is right in the middle. Okay, and we can see now that beta 2 out of all three guesses, right, is even closer to the optimal value beta star relative to our other iterations, right? That error now is really, really small. We're getting really close to zooming in and honing in on that solution. Note that beta 0 was the furthest, right? Iteration 0, we had the furthest guess, right? Largest distance. Okay, but then we updated. We said, oh, we're too far to the left. We need to move that goalpost. We moved the lower bound to the right. And then we improved our guess by bisecting again. Beta 1 was a little bit closer here. Okay, but of the three guesses at this point, beta 2 was absolutely the closest. It has the smallest distance between the guessed parameter value and the actual parameter value. So you can imagine here, if we keep on iterating, we keep doing this, beta 3, beta 4, beta 5, right, all the way to, let's say, t iterations, at some point, okay, we are going to converge to the solution, right? We started pretty far away, but we slowly improved. Okay, so after t iterations, our guess is going to be even closer, and we could even go farther here and argue that if in the limit we allowed t, the number of iterations, to go to infinity, then certainly we are going to close in on the optimal parameter value beta star here. So this is the idea behind the iterative algorithm, that if we do this repetition enough, we will converge to a solution. Okay. Unfortunately, right, we don't have the time to really undertake an infinite number of iterations. It would take a very, very long time to do that. But fortunately, the computer is handling that repetitive process, so we could have the computer do millions of iterations very quickly here, not an infinite amount. But the idea is we are going to take enough iterations. Okay? We're going to do enough repetitions to the point where after iteration t, our estimates, which is the beta value in that iteration, they will be sufficiently close. Okay? They will be sufficiently close to the actual true parameter value beta star that minimizes that cost function. Now, how close is close enough? How do we know when we've gotten there? Well, in order to figure that out, we're going to apply something called a stopping rule. And a stopping rule will tell us essentially how close we need to be in order for us to exit the repetitions in those iterations, stop, and report the current guess as our best guess of the optimal value. So there's a few things to take note of when we get near the optimal value for beta. Okay, first thing to note is that the change between guesses starts to get smaller, right? The distance between beta 0 and beta 1 was a little bit bigger than the distance between beta 1 and beta 2, right? Okay, so one common stopping rule is to say, hey, let's exit the iterations once the difference between the parameter values at any two iterations become sufficiently small. Okay, so if I see between iteration t and t plus 1 that the beta value doesn't change that much, that must mean we are pretty close. And we're going to use this number epsilon over here to refer to a very, very small number, maybe like 0.00001 or something. It's a tolerance level that is going to define for us how close is close in order for us to stop and exit the iterations. Okay, the smaller that tolerance is, the longer the algorithm is going to take, because it's going to make those betas get really, really close before it says, okay, we are sufficiently good here. All right, now this is not the only stopping rule. There are many different types of stopping rule criteria. Okay, the other thing to note when we get closer to beta star is that the upper and lower bounds at each guess also become smaller at every iteration, right? Okay, the upper bounds at iteration 0 are really wide, but then they get smaller, smaller, and smaller. So another rule that will work would say, hey, let's go ahead and squeeze those upper and lower bounds together until they become sufficiently small in distance. So if the upper and lower bounds become sufficiently close, then we know we are bisecting sufficiently close to the optimal solution. So this is an alternative stopping rule that would get the job done as well. Okay, right, between the initial guesses, right, initialization boundaries, we were all the way out here, right? But after one iteration, that boundary was cut, right? Our upper and lower bound distance shrank. Okay, and after the second iteration, that distance shrank even more. Okay, another observation you might notice is that when we get towards the optimum here, when we get towards the bottom of this function, okay, the slope of the tangent line as we get towards the bottom of that function becomes flatter. Okay, so near the minimum, right, the cost function's value, it does not change as much since the slope of the cost function flattens out and becomes close to zero. So there are a few different ways of recognizing what we refer to here as the first order condition being satisfied, right? If we're very far away from the solution, then the slope of the tangent line is very far from zero. But as we move closer to the solution, that tangent line flattens out, right? At beta star, what happens? It gets exactly equal to zero. But as we move away, then that tangent line becomes steeper in magnitude in either the positive or the negative direction. So we could think about here formalizing this first order condition, right? By saying, hey, let's go ahead and look at a stopping rule where either the value of the cost function doesn't change that much between iterations, okay, or we could look at a stopping rule that says, hey, if that slope is sufficiently small enough, if the magnitude of that derivative is small enough, it's close enough to zero, then we can go ahead and stop. All right, so we've looked at a couple different stopping rules here. One uses the changes in the guess value at each iteration. When those changes become small enough, we exit. These stopping rules that we're looking at here require us not to assess the guess at every iteration, but they require us to assess some property of the cost function, either the value of the cost function itself or how much that cost function has changed from the derivative. So before we wrap up here, just a few things about the stopping rule. First thing to understand here is the value of epsilon here. This thing is an arbitrary constant that the user has to specify, and the smaller epsilon is, the harder the stopping rule criteria is to satisfy. The algorithm will take more iterations in order to converge if you use a smaller epsilon. The upside of this is that if we stop at iteration t, okay, if we wind up exiting because we satisfy that stopping rule criteria, then beta t will be relatively closer to the true value beta star because we forced it to go through more checks. We've moved closer. Okay, if epsilon is larger, okay, then it is easier for us to implement the stopping rule criteria, and that's not necessarily a good thing. The positive is that the algorithm will take fewer iterations to stop because we're not requiring things to move closer together, right? The epsilon's allows them to be a little bit farther apart. And if that happens, if we stop too early, then our estimated parameter beta t at iteration t will be relatively farther from the actual true value. Okay, so let's go ahead and discuss here the full structure of the bisection algorithm. Okay, step one, in initialization, we are choosing the initial guesses for the boundaries, the upper and lower bound at iteration 0. And then we move into the iterations. Okay, starting with t equals 0. So at each iteration, starting at iteration 0, we're going to compute our guess by bisecting. Okay, and then we're going to do the check for the slope. We check the slope of the cost function. Okay, and we're going to use that check on the slope to update our guess here. So then we move on to element 3, which is the update rule. And we recognize if the derivative is positive, okay, if the derivative is positive, then we were too far to the right. Right? If we were dealing with this positive derivative case, then we were too far to the right. And in that situation, we wanted to move the upper bound to the left. Okay, so this is us moving the upper bound to the left. We set the upper bound in the next iteration equal to the guess at the current one. Conversely, if the derivative is negative, if the function is sloping downwards at the point we check our guess, okay, then we're going to do the opposite. We are going to take the left boundary point and we're going to move it farther to the right. Okay, so that updated our rules. And then what we do before we exit and move on to the next iteration, we check, do we meet the stopping rule criteria? Okay, if the stopping rule criteria is met, and we could use any of those stopping rules, maybe the beta is changing very small, or maybe the value of the cost function's change is very small, or the slope of the cost function is close enough to 0, where we would exit. If we do satisfy the stopping rule criteria, then we're going to exit and we report beta t at that iteration. Otherwise, if we do not meet that stopping rule criteria, meaning the cost function is changing enough or the guess parameter is changing enough, then we're going to go back to step 2 and we're going to keep repeating those iterations with our updated guess. Okay, we're going to keep repeating. We go back to step 2, we bisect, we check the derivative, we update, we check the stopping rule, and we keep doing that as long as the stopping rule is not satisfied. Okay, now, just a couple disclaimers here. Things can go wrong, as we've mentioned. Okay, first thing that can go wrong is you could have a problem with your initial guess. We saw that the initial guess could give us bounds outside of the solution range. Okay, and in that case, we would never find the optimum. We would be converging, every period we would see the algorithm does not converge. We're guessing forever. And there's ways around this. And there's ways around this. You can actually loop the search over multiple guesses. There's actually a way we can deal with this using a stochastic version of this method, which randomly chooses the initial point rather than having the user specify it. But that creates some other problems as well. And we'll get to that when we talk about gradient descent. But this is one problem we can run into. The other problem we can run into is we could have a function, a cost function rather, that is highly nonlinear. Right, we were dealing here with a cost function initially that had a very nice shape. Is that right? Very nice shape. Okay, we had this cost function that was perfectly concave upwards, right? And if it looks like that, we know we're going to wind up with an optimal solution. But the problem is you could get a cost function that looks funky. Excuse me. Could have a cost function that is multiple optimum, that goes up and down. And the question is, well, if that happens, how do we know which optimum we are finding, right? We might find a local minimum that's not a global minimum. And there are ways around this problem. We'll talk about how we can overcome this by implementing the stochastic gradient descent algorithm a little bit later, in a later segment. But there are a large class of problems that do have these well-defined concave cost functions, concave up cost functions, as we've described. So this is a problem that you could deal with. You could have a highly nonlinear cost function. Another problem you could deal with is you could have a cost function that tends to be very flat, okay, near the optimum. And this can cause a problem for some stopping rules. If the function is very flat, okay, our stopping rule, if it's predicated on checking the derivative or the change in the cost function, we might see, oh, the derivative is really close to 0, and we exit, but we're not actually near the right parameter value. We just found a part of that cost function that was flat. And this can cause us potentially to exit too early. Okay, we can exit too early, which means we'll have more of an incorrect or more error in our parameter estimate here. The other problem that we could have is if we are checking the change in the parameter value at each iteration, okay, we could hit a flat portion where it takes maybe too long to converge. We're near the solution, but we're seeing that the beta is changing quite a bit because that function is really flat. And we could wind up in the opposite situation where it takes too long for our iterative algorithm to converge to a solution. Last problem that we're going to see, and this is actually not a problem with this particular bisection algorithm, but we are going to run into this problem potentially in the gradient descent framework. When you update your guess, this could result in jumping between guesses in a way where the jumps are maybe too big and you wind up bouncing up the cost function instead of going down it. Or the jumps are too small, which means every update you could have updated more aggressively, and it's going to take a lot longer for the algorithm to actually converge to a solution. So these are just a few problems, things that can go wrong here to be aware of. Not everything is always ideal. And this takes a little bit of finesse, some trial and error to pin down an iterative approach. So this was the bisection algorithm. We're not really going to use this one or code this one up in practice, but this is a good building block for understanding the elements of an iterative algorithm, specifically for us to move into a case where we have to choose multiple parameters at the same time. We have a multivariable iteration problem to solve, a multivariate optimization problem. And in that case, we're going to use the gradient descent algorithm, which is really a multi-dimensional framework to think about applying the bisection approach with a few cosmetic differences. But the general idea is the same. At every iteration, we're going to use some information about the slope of the cost function to update our guess, to improve that guess, and then check some stopping rule criteria at every iteration until we think we are sufficiently close to the proper parameter estimates. So I hope that made sense. Stay tuned for another segment on gradient descent, and I will see you shortly.